It's amazing. Like, we keep building these super advanced language models, and we kind of just expect them to, perfectly absorb and remember tons of information. But the reality is, they have these inherent limits, especially if you throw really long or complicated contexts at them.
Yeah, it's like they kind of start to forget the earlier stuff.
Right. And the responses can get kind of wonky, not as sharp as we'd want.
Exactly. And that actually points to like a huge challenge in AI development overall, right? Like, how do we actually make these models really good at handling, massive amounts of context and using it effectively? It's a tough nut to crack.
It really is. But speaking of cracking nuts, a brand new research paper today that offers a pretty interesting approach to this whole context problem.
Yeah, for sure.
So today we're diving deep into Resona, improving context copying in linear recurrent models with retrieval. Now, a lot of our listeners are probably familiar with transformer model.
Right, the big players these days.
Yeah, they power a lot of the language tech we see, but there's this growing interest in exploring linear recurrent models, or LRMs, as maybe a more efficient alternative.
For sure. And for good reason.
Yeah, so why are LRMs potentially more efficient?
Well, unlike transformers, which use attention mechanisms across the entire input, every word attending to every other word, LRMs worked a bit differently. They process information sequentially. They kind of compress the context into this fixed size hidden state.
Ah, so it's like summarizing a whole book into a single paragraph.
Yeah, exactly. You got it. And this sequential way of doing things leads to much faster inference. That's a huge deal for all sorts of real-world applications where speed is key.
I can see that, but I'm guessing this comes with a trade-off, like squeezing all that context into a fixed space. It's got to have some downsides.
Absolutely. And that downside is exactly what the researchers call an information bottleneck.
Information bottleneck.
Yeah. Think of it like this. You're trying to explain this super complex idea to someone, but you can only use like 5 words. You're going to miss a lot of the nuances, right?
Makes sense. You can't capture everything.
Exactly. And that's the problem here. When you have this fixed size hidden state and you're feeding it, longer and longer, more complex inputs, something's going to give. And what gives is often the model's ability to recall specific details or make those subtle connections, especially for in-context learning, where it needs to learn from examples right there on the prompt.
Ah, so it's not just about remembering a long list of facts. It's about understanding how those facts relate to each other within a specific context.
You got it. And the researchers actually put this limitation into a very concrete mathematical form with something they call Lemma 3.1. Basically, what it shows is that if you have more possible input states than your hidden state can represent, you're guaranteed to lose some information.
It's like you have this giant library and you're trying to fit all the information into a tiny little card catalog.
A perfect analogy. You're going to have to make some tough choices about what to keep and what to toss.
Okay, so we've got this inherent memory limit in LRMs. Now, how does Resona try to get around this? Like, what's the main idea?
Well, Resona comes in and says, hold on, what if we give LRMs a way to access the original information directly? Kind of like a cheat sheet. We don't have to cram everything into that tiny hidden state if we could just go back and look at the source when we need to.
So it's like giving the model a way to reread the important parts of the text when it's trying to figure something out.
Exactly. It's all about improving how these LRMs actually use the context they're given.
This sounds like a really clever approach. And that's our mission today. We're going to dig into Resona, figure out how it works, why it's such a big deal, and what it might mean for the future of efficient language models. Are you ready to dive in?
I'm ready. Let's do it.
Okay, so before we get into the nitty-gritty of Resona, can we take a step back and talk more about why LRMs are actually more efficient in the first place? You mentioned they process information sequentially, right? But how does that translate into actual computational savings compared to transformers?
Sure. So think of transformers like a huge team meeting. Everyone's talking to everyone else all the time, trying to figure out what's going on. That's like the attention mechanism. Every single word in the input is paying attention to every other word.
Lots of crosstalk, lots of information flying around.
Yeah, exactly. And that can be really powerful for understanding complex relationships between words and ideas. But it comes at a cost. The more people you add to the meeting, or the longer the text you feed the transformer, the more chaotic and time-consuming it gets. Computationally speaking, it scales quadratically, meaning the time and resources needed grow much faster than the length of the input.
Aha, so for really long inputs, transformers can get bogged down.
Right. Now, LRMs are more like someone reading a book and taking notes as they go. They go through the text word by word, updating their understanding with each new piece of information. They keep a running summary in their head, that's the fixed size hidden state, but they don't have to constantly compare every single word to every other word.
So it's more of a streamlined linear process.
Exactly. And because of that, the computational cost scales linearly. It grows at a much more manageable pace as the input length increases. That's why LRMs can be so much faster and less memory hungry, especially when dealing with really long texts.
Okay, I think I'm starting to see the appeal, but as we discussed, this efficiency comes at the price of that information bottleneck. Could you explain a bit more about why this fixed size hidden state is inherently limited when it comes to remembering and using information? Like, why can't it just hold more?
It's a good question. It's not just about the size of the hidden state, it's about what it has to represent. Imagine you're trying to summarize a complex novel in a single sentence. You could probably capture some basic plot points or character, but you'd miss all the nuance, the character development, the subtle themes, right?
Right, all the richness of the story would be lost.
Exactly, and that's what happens with LRMs. As the input gets larger and more complex, the fixed size hidden state has to cram more and more information into the same limited space. The paper actually puts it well. However, this unified representation has been shown to also act as an information bottleneck, where the number of potential elements in the vocabulary cannot be properly maintained within a state that does not grow with the possible combinations of tokens.
So it's not just the length of the text that matters, but the variety and complexity of the information it contains.
Precisely. The more diverse and intricate the input, the harder it is for that fixed size vector to accurately capture everything. And this is a huge problem for in-context learning, where the model needs to not only remember the examples in the prompt, but also understand the connections between them. That's why LRMs have traditionally struggled to match the performance of transformers on these kinds of tasks.
Okay, so that all makes sense. Now, before Resona came along, were there any other attempts to solve this context problem, either with LRMs or with transformers, like to make them better at handling longer sequences?
Yeah, there have been a lot of efforts to improve both types of models. For transformers, people have experimented with things like sparse attention, where each word only pays attention to a few key words instead of all of them. And there are memory-augmented architectures, basically adding external memory to the model. And even some folks have tried making transformers more recurrent, borrowing ideas from LRMs.
So a lot of different ideas on the table.
Right. And with LLMs, there hasn't been as much direct work on this specific bottleneck, but the paper does make a distinction between Resona and retrieval augmented generation, or RAG.
Oh yeah, RAG, we've talked about that before. That's where you use an external database to provide more information to the language model, right?
You got it. So with RAG, you basically have this separate knowledge base, and the language model can search through it to find relevant information. But the key difference with Resona is that it's not pulling information from some external source. It's specifically retrieving information from the input text itself.
Ah, so it's like saying, hey, I remember reading something about that earlier in this document. Let me go back and check.
Exactly. It's not relying on some outside knowledge. It's improving how the model uses the information it's already been given.
That makes sense. So RAG is more about adding new knowledge, while Resona is about better utilizing existing knowledge.
You got it.
Okay, so let's get into Resona. How does this thing actually work? Like, what are the main components that make this retrieval magic happen?
So the paper describes Resona as a simple and scalable framework for augmenting linear recurrent models with retrieval. And it's built on this really cool idea. Let's bypass the bottleneck by giving the LRM a way to directly access and integrate the most relevant parts of the input context.
Sounds promising, but how does it do that in practice?
Resona basically has two main parts: contextual search and knowledge immigration. It's like a two-step process for finding and using the right information.
Okay, a two-pronged attack on the bottleneck problem. Let's start with contextual search. How does that work?
So imagine you have a long document. The first thing Resona does is chop it up into smaller chunks of text. Then it uses the LRM's hidden state, that compressed summary of its current understanding, as a query. And it has this retriever mechanism that compares this query to all those chunks of text it created.
So it's like the LRM is saying, based on what I know right now, which parts of this text seem most relevant to me?
Exactly. And it's looking for the chunks that are semantically closest to its current state. The paper outlines this process in Algorithm 2, where they talk about chunking the input, encoding the chunks in state, and then calculating similarity scores, often using something called cosine similarity.
Cosine similarity, is that just a fancy way of measuring how similar two things are?
Yeah, exactly. It's a way to compare the direction of two vectors so you can tell how much they point in the same direction, which in this case means how similar they are in meaning. And the output of this whole search process is an attention mask, which basically highlights the chunks the reader thinks are most important. And just to make it even clearer, figure 3 in the paper shows a nice diagram of how this whole chunk and search thing works.
Okay, so the LRM has basically created a spotlight on certain parts of the text, like saying, pay attention to this.
Yeah, exactly. It's like highlighting the important sentences in a textbook.
So what happens to those highlighted chunk? That's where knowledge integration comes in, right?
Right. So now we have these chunks that the contextual search has flagged as super relevant. Knowledge integration is all about taking that information and actually weaving it back into the LRM's output.
So it's not enough to just find the relevant information. You have to actually use it.
Exactly, and that's where a cross-attention module comes into play. Now, in this stage, the LRM's hidden state again acts as the query, just like in the search. But this time, the keys and values for the attention mechanism come from the initial embeddings of the input tokens.
Wait, hold on. Embeddings. Remind me what those are again?
Sure. So before a language model can process words, it needs to convert them into a numerical representation that it can understand. These representations are called embeddings, and they basically capture the meaning of words as vectors or points in a high-dimensional space.
Ah, so it's turning words into numbers that the model can crunch.
Exactly. And the cool thing is, words with similar meanings end up having similar embeddings, so the model can understand relationships between words based on how close their embeddings are.
Okay, so back to knowledge integration. We're using the hidden state as a query and the initial embeddings as keys and values.
Right. And what happens is that the attention mechanism is now focused specifically on the chunks that were identified as relevant in the contextual search. It's like the LRM is saying, okay, now that I know which parts are important, let me really focus on understanding those parts.
It's a very good approach to incorporating information.
Exactly. And the whole process is laid out in algorithm 3 in the paper. They talk about calculating the queries, keys, and values, applying the masked cross-attention, and then doing a final projection step. And if you're more of a visual learner, figure 4 in the paper shows a nice illustration of how this integration works.
Okay, so we searched for the relevant information and we've integrated it back into the LRM's output. What happens next?
So you have the output from the knowledge integration module, which they call MathBF, and you have the original output from the LRM layer, which is MathBF. And they combine these two outputs using a weighted sum, which is a fancy way of saying they take a bit of each and add them together. The formula looks like this: MathBF plus 1.
So it's blending the original output with the new contextually enriched output.
Exactly. And that alpha dollar symbol, that's a weighting factor that determines how much of each output to use. It can be a fixed value, or it can be dynamically adjusted based on the input.
Okay, that makes sense. So it's like fine-tuning the balance between the old and the new.
Precisely.
So Resona seems like a pretty clever way to give LRMs a boost. What are some of the things that make it so innovative, and what are the big advantages the researchers highlight?
Well, I think one of the coolest things about Resona is how it tackles this bottleneck head on. It doesn't try to redesign the LRM completely or invent some newfangled architecture. It just adds this clever retrieval mechanism that works within the existing framework.
So it's like a surgical enhancement, not a complete overhaul.
Yeah, I like that analogy. And it's designed to be really efficient. Remember how we talked about the importance of parallelism for speed? Well, the beauty of Resona is that all this chunking, retrieving, and integrating happens in parallel with the normal LRM computations. It doesn't add a ton of overhead.
So it's getting the benefits of better context handling without sacrificing the efficiency.
Exactly. And another really clever thing is how they use causal masking during training. Basically, this ensures that when the retriever is searching for relevant context, it can only look at information that came before the current point in the text.
Ah, so it's respecting the sequential nature of language. You can't look ahead in time when you're processing text.
Precisely. It's like making sure the LRM isn't cheating by peeking at the answers in the back of the book.
Smart. Are there any other advantages worth mentioning?
Yeah, Resona is designed to be pretty modular, so you can actually plug it into different types of LRMs. It's not tied to one specific architecture.
So it's like a universal upgrade for LRMs.
Exactly. And they've even put some thought into making inference efficient, too. They have this dynamic chunking strategy where the size of the chunks can change depending on the input. And for really long prompts, they suggest you could even integrate the retrieval into the filling stage, so it's all done ahead of time.
So they've really thought about making it practical for real-world use.
Yeah, definitely.
Okay, so we've talked a lot about how Resona works. Now let's bring RAG back into the picture. You mentioned that one of the key differences is that Resona operates within the input context, while RAG relies on external knowledge. Why is that distinction so important? Like, what are the theoretical implications?
From a research perspective, it gets to the heart of what Resona is trying to achieve. The paper puts it this way: RAG is not directly applicable for learning texts, as such methods do not search within the input-specific query, but rather from an external database, nor do they account for the information bottleneck with LRMs. So basically, Resona is all about improving the LRM's ability to understand and utilize the information it's already been given. It's directly tackling that inherent limitation we talked about, that information bottleneck caused by the fixed size hidden state. RAG, while powerful, is more about supplementing the model's knowledge with external information. It's not addressing the internal mechanism of how the model processes context.
Right. So Resona is more about improving the model's internal memory and understanding, not just giving it more facts to work with.
Precisely.
Makes sense. The paper also talks about the relationship between Resona and these other hybrid architectures like Mumberformer and Himba. Where does Resona fit in with those kinds of models?
Yeah, so these hybrid models are becoming increasingly popular, and they kind of try to get the best of both worlds. They combine recurrent layers, like the ones in LRMs, with attention layers, like the ones in transformers. The idea is to leverage the strengths of each approach.
So a bit of a mixed bag, trying to find the optimal balance.
Yeah, exactly. And the paper actually suggests that you can think of Resona as a kind of hybrid approach, too, they say. Similarly, Resona can be interpreted as a form of hybrid mixture of attention and recurrence, with the difference lying in the frequency of attention and its sparse within different layers. So instead of having full attention everywhere, Resona strategically introduces attention in specific places, guided by the retrieval mechanism.
So it's like a more selective and efficient use of attention.
Exactly. It's not just blindly throwing attention at the problem. It's using retrieval to figure out where attention is most needed. And that makes it a really interesting addition to the whole hybrid model landscape.
Okay, so Resona sounds pretty good in theory, but does it actually work in practice? What kind of results did the researchers get?
Well, they did a pretty thorough job testing Resona on a bunch of different benchmarks. They looked at synthetic tasks, standard language modeling tasks, and even some question answering tasks.
Okay, let's start with the synthetic tasks. What were those like?
So these tasks were designed to really probe specific capabilities of the models. One of them was the multi-query associative recall, or MQAR task, basically a memory test. You give the model a long sequence of information, and then you ask it questions that require it to recall and connect different pieces of information from earlier in the sequence.
So it's really how well the model can hold on to information over long distances.
Exactly. And the results were pretty impressive. Figure 5 of the paper shows that Persona augmented LRMs did amazing on this task. They got near perfect accuracy, even as the sequences got longer and longer. Well, the baseline LRMs just completely fell apart.
Wow, so a pretty clear demonstration of Resona's effectiveness.
Yeah, for sure. They also tested on this benchmark called the EMAD suite, which has a bunch of different tasks designed to look at things like retrieval, compression, and memorization. And Table 1 in the paper shows that Resona consistently improved retrieval across all these tasks. It even helped with compression and memorization in some cases.
So it wasn't just good at one specific thing, it had broad benefits.
Exactly. And importantly, they found that Resona didn't make things worse on tasks where the original LRMs were already doing well. So it's not like it was making trade-offs, it was just improving things across the board.
Okay, so it's not a case of one step forward, two steps back.
Nope. It seems like all steps forward.
Sounds promising. What about the standard language modeling benchmarks?
They tested on the Wikitext 103 dataset, which is a pretty common benchmark for language modeling. And Table 2 shows that model Resona consistently got lower perplexity scores than both baseline LRMs and models with a similar number of parameters.
Remind me again what perplexity measures.
It's basically a measure of how surprised the model is by the next word in a sequence. So a lower perplexity means the model is better at predicting what's coming next, which indicates a better understanding of the language.
Okay, so Resona is not just helping with memory, it's actually improving the model's overall language understanding.
Exactly. It's not just about remembering facts. It's about making sense of the language as a whole.
Cool. What about the question answering tasks? Those seem like a pretty good real world test.
They tested on a few different datasets like narrative QA, co-QA, and trivia QA. And they looked at a bunch of different metrics like Blue U, Rougel, Meteor, and F1. And across the board, they found that adding Resona to pre-trained Mamba and Himba models led to better performance.
So it's helping these models reason about the text and answer questions more accurately.
Yeah. Table 3 in the paper shows all the details. They even compared Resona to some simpler methods that just append retrieved context to the input, kind of like a basic form of RAG. And Resona consistently outperformed those approaches, which shows that it's really the integration part that makes the difference.
So it's not enough to just give the model more information. You have to make sure it knows how to use it.
Exactly. They even compared Resona to other hybrid models, like Humba. Table 5 shows that in some cases, replacing the attention components in Humba with Resona actually led to better performance especially on tasks like CoQA. So that suggests that Resona's approach might be even more robust and effective than some of these existing hybrid methods.
Wow, that's a pretty strong statement.
Yeah. And if you want even more evidence, check out the appendix. They have results on this needle task, which is all about finding specific information in super long texts. Table 7 shows that Resona is really good at that. And they also show in Table 8 that Resona doesn't mess up the model's ability to do zero-shot language modeling, even after you fine-tune it on other tasks. So it seems like a pretty safe and effective upgrade overall.
Okay, so the empirical results are pretty convincing. Resona seems to live up to the hype. From a more academic standpoint, what do the researchers highlight as the big contributions of this work?
Well, I think one of the biggest things is just the introduction of Resona itself. It's a novel framework for addressing a very specific and important problem in LRMs, and they back it up with a solid theoretical foundation. Remember Lemma 3.1, which formalized the information bottleneck? That lays the groundwork for why Resona is needed in the first place. And then they test it rigorously on all these different tasks and models, showing that it actually works in practice.
So they've identified a problem, proposed a solution, and then demonstrated that the solution works.
Exactly. It's a very complete piece of research, and they really emphasize the efficiency aspect. They've designed Resona to maintain the computational advantages of LRMs, which is crucial if we want these models to be practical for real-world use.
Right, efficiency is king, especially as these models get bigger and bigger.
Absolutely. And ultimately, I think their main point is that Resona offers a new path towards making LRMs more competitive with transformers, especially when it comes to tasks that require understanding and utilizing large amounts of context. They're bridging the gap between efficiency and performance.
So it's a big step forward for LRMs.
Yeah, I think so.
Okay, so to wrap up this deep dive, what's the main takeaway for our listeners? What should they remember about Resona?
I think the key takeaway is that Resona represents a significant breakthrough in our ability to make linear recurrent models more powerful and more effective. It directly addresses a fundamental limitation of these models, that information bottleneck we keep talking about, and it does so in a clever and efficient way.
Right, and it all boils down to these two core mechanisms, contextual search and knowledge integration.
Exactly. By giving LRMs the ability to selectively retrieve and integrate relevant information from the input context, Resona unlocks a whole new level of performance, especially on tasks that require understanding and utilizing complex, long-range dependencies.
It's like they've given LRMs a superpower.
In a way, yes.
So this research has some pretty exciting implications for the future of AI. What are some of the things that you're most excited about?
Well, I think one of the most intriguing possibilities is that Resona could help usher in a new era of language models that are both extremely powerful and remarkably efficient. If we can achieve near transformer-level performance with the computational benefits of LRMs, that could open up a whole world of new applications.
Especially for applications where resources are limited or where speed is critical.
Exactly. Think about things like mobile devices, or real-time translation, or analyzing huge data sets in a matter of seconds. And it could also make these powerful language models more accessible to a wider range of researchers and developers, which could accelerate progress in the field as a whole.
It feels like we're on the cusp of something really transformative.
I think so too. It's a very exciting time to be working in this field.
And on that note, for all our listeners who want to dive deeper into Resona, we highly recommend checking out the full research paper. It's packed with even more details and insights.
Yes, definitely. It's a great read.
Thanks for joining us on this deep dive into Resona. It's been a fascinating journey. We can't wait to see what the future holds for this technology.